Good morning, everyone, or good afternoon, depending on where you're tuning in from. Uh, we're going to begin today's webinar, the topic being Short Circuit Result Analyzer. I'm Steven Chagoya, and I'm a Senior Power Engineer here at ETAP Operation Technology. So before we begin, I just want to remind everybody to sign up for the user conference, April 20th to 22nd. 2015. Okay, so let's go ahead and begin today's session. I want to start off with just some basic concepts, so as a refresher for everyone. So what's a short circuit? Well, a short circuit is a low impedance abnormal contact between 2 points of different potentials. A short circuit duty, which is what we use ETAP to evaluate protected device capability, is the maximum available short circuit fault during the first half cycle or interrupting current. So what kind of faults do we have? Well, as many of you already know, we have a three-phase ungrounded fault, three-phase grounded fault, face-to-face ungrounded fault, face-to-face grounded fault, and a face-to-ground fault. Now for this session, we will be only focusing on three-phase faults. These are, for the most part, the worst case faults that can occur because you're essentially demanding three phases of power from your sources. Again, these three-phase faults are very rare, and the most common faults involve one or two phases of the circuit. But you still have that risk or that probability of it occurring, so you want to make sure that your devices are properly sized. So the short circuits have negative effects to your system and to your equipment. You can have insulation damage, mechanical damage from the electromagnetic forces. You could also have arc flash and arc blast events. And some faults can also lead to system instability. So a short circuit duty study will be used to determine the following, which is you want to verify protected device closing and latching capability. You want to verify protected device interrupting capability. You want to make sure that the equipment is properly sized so that it can endure mechanical forces from the peak currents. You also want to make sure that it can withstand any thermal stresses, or I squared T. And you also want to verify your relay coordination. So you would need your minimum short circuit for coordination. So in ETAP, the systems that are involved in short circuit calculations are your power company supply, which is your utility connection, any in-plant generators, transformers, and if you have any tolerances, you can go ahead and input those, and these will basically reduce your transformer impedance so that you could consider a higher short circuit. The same goes for reactors and feeder cables and bus duct systems. Again, for cables, you're going to want to also consider any lower temperatures so that you can adjust the resistance. The same goes for overhead lines, synchronous motors, induction motors, protected devices, and also consider the shunt from static loads and from the capacitance and lines. Now, at this point, I'd like to go over the short circuit phenomena, just so that we can highlight the the components involved in the short circuit. So as you know, the short circuit is represented as a Thevenin equivalent with a voltage source, which is your pre-fault voltage at the bus fault location, with an equivalent resistance and equivalent inductance or reactance. The instantaneous voltage is determined as the resistance times the instantaneous current passing through it, plus the inductance with the rate of change in current. This gives you the voltage magnitude with the sinusoidal component. If you were to solve this equation, you'll get the instantaneous current. You get the voltage magnitude divided by the magnitude of the impedance, which is just the magnitude of the current, with a sinusoidal. This is going to be your AC component. Then you're going to have your DC component, which is basically determined here from your exponential decay, from your X over R ratio of the system. So what do the waveforms look like? Well, you have here the AC symmetrical, or when you're doing evaluation of your components, you're going to be looking at the symmetrical current. Now the DC decay, as shown here in the blue curve, will be needed to find the instantaneous and also for the asymmetrical current. Let's go ahead and show the asymmetrical current here in the next slide. So this is your asymmetrical current. You also want to verify that your device or your equipment can withstand this current. And it's just your AC symmetrical on top of your DC decay. And it's shown here with the red curve. Now, when determining for HVCBs and for some medium voltage buses, you want to be looking at the peak current. So you want to make sure that it can withstand the full mechanical force that occurs during the short circuit phenomenon. And this is your instantaneous current. This is just your AC and your DC together, including decays. It's shown here as your red curve. Now for today's webinar with the short circuit result analyzer, we're going to be focusing only on ANSI, three-phase systems, and buses, low voltage and medium buses. In the future, the short circuit result analyzer will have a capability of doing both ANSI and IEC standards, three-phase, single-phase systems, low voltage, medium voltage, high voltage buses, high voltage circuit breakers, low voltage circuit breakers, fuses, and switches. Okay, so let's go ahead and move on to the ETAP interface. So when doing your short circuit studies, you want to consider various scenarios or configurations. You want to be looking at your minimum faults for coordination of your low voltage breakers and your relays and fuses. And you want to be looking at your maximum current so that you can verify if your equipment is properly sized. If you're doing a system analysis or if you're going to be doing a design, you want to make sure that you select devices that can withstand that maximum available fault. So in ETAP, you can set up all your scenarios just using your revision, configuration, and your study cases. So for the revision, this basically allows you to modify any input data. So you can modify anything that you enter into the editors. You could have various cases of those. So for this example here, I'll be using 2 revisions, which is just my base, and then I've created a new revision for utility minimum. Now in my utility minimum revision, what I've done is that I've entered a minimum available fault current from the utility, which is shown here. So here I have a 17.2 kA. So if you're dealing with utility, you want to make sure and ask them for your minimum and maximum faults so that you can enter this in ETAP. Now in my base, I've went ahead and entered my maximum available fault from the utility, and you can see here that it's 20 kA. Now as far as configurations, these are very dependent on what your system looks like or your system type is. For example, if you have a large commercial facility, you may want to consider standby power configuration, an alternate utility supply configuration, as well as parallel operation. So if you're going to be operating with both utilities or a generator and a utility. If you have like a large or a medium-sized industrial complex, you may want to consider secondary selective. The outage of a transformer, like in a main tie main, outage of a cogenerator, operations with tie circuit breakers, an islanded configuration if you're just going to be operating the facility with your in-house generation unit, and also any standby power sources. If you're dealing with substations or distribution system, you want to consider any alternate supplies and any loops involved, so any switching configurations that you have in the switching units. And for this example here, I've done 3 configurations, and I'm basically considering cogeneration, which is as you see right now on the screen, utility with my generator in service. I've also configured an emergency in the case that I'm just energizing the system with my in-house generator, and then normal operation if I'm just operating the facility with the utility incoming. Now as far for the study cases, let me go ahead and show you how you would set up your minimum and maximum. These are required when doing your short circuit duty analysis. So let's go ahead and go over the minimum. So if I enter my study case, I've already explained that I have used a revision data so that I can input a minimum current available from utility. So now in the study case, there's a couple of options that you need to set. First, you want to include any equipment cables or overload heaters in this section here. You also may want to consider not supplying any motor contributions. So what I've done here is that I set my loading category to shutdown, and I know that in shutdown for all my motors I've set to 0%, meaning that they're not going to contribute any fault current. Now in standard, what I've done is that I've reduced the pre-fault voltage just slightly. I've set it to 99% here. Of course, you can set it to whatever you wish. Now under the adjustment page, what I've done is that I've neglected any impedance tolerance adjustments, any length tolerance adjustments, and also any resistance corrections. So just go ahead and disable all of these checkboxes. Now let's go ahead and navigate to the duty maximum and go to the info page. Okay. So here's my maximum study case. So what do you do to set up a maximum study case? Well, what you want to do first of all is you want to exclude any equipment cables from your loads or from motors. Just go ahead and uncheck these options. because you don't want to include any additional impedance between your machinery and your fault. You want to consider as much short circuit available fault. Also, the other thing that you need to do is I like to set here under motor contribution based on both. And set your loading category to design or normal, anything where you have any percent loading for your motors. This will make sure that all your motors are being considered as contributing sources. Now for the standards page, you can do is raise the pre-fault voltage. So you can raise it up to 105. This is just going to increase that current magnitude. Again, this is user definable, and you can set it to as much pre-fault as you need, up to 10%. Now under the adjustments page, you want to go ahead and make sure you're either doing a per individual element impedance tolerance, length tolerance, or resistance corrections. What I've done here is I've just added global. You can set a global tolerance for transformers, reactors, and then the length of cables. All of this is going to make sure that you're reducing the impedance from these branches so that you can consider more short circuit fault downstream from your sources. Now, as far as the alerts, you can just set them as default. I'll go ahead and show you what the result analyzer, what tool now it now has. So this is not very critical right now. So go ahead and press OK. Now that you've set up your revision data, now you have your different configuration schemes, and then you have your minimum and maximum study cases. You can set up your scenarios so that you can consider all possibilities. I've already set up 4 scenarios here. I have my maximum emergency using base, emergency configuration, and duty maximum. And I'm making sure I'm running an ANSI device duty. I have also my maximum, my minimum emergency, and my minimum normal. Now I'm going to go ahead and add up a new scenario, and I'm going to set this one up to be my cogen minimum. So I'll start off with my revision set to utility minimum, configuration at cogen, study type is ANSI duty, and now I set up my duty minimum, and I can give a unique name to my output report, and I can press OK. Now all I have to do is make sure that my macro is set up, and I have here my 4 scenarios, the emergency maximum, maximum, minimum emergency, minimum normal, and I'm just going to go ahead and add the 5th scenario that I created right now, which is scenario 1, which was my minimum cogen. And I'll just go ahead and execute this one. Okay. Now I'm just going to go ahead and launch the short circuit result analyzer. And it's going to be located on your right hand toolbar right underneath the report manager. And as you can see here, all my reports for my scenarios have been loaded in, and I'm seeing some nice alerts here and any result information. So let's go ahead and give just a tour on the analyzer. Here on the top left, we have our study reports. You can select either ANSI to look at all your ANSI reports, or if you're doing any international studies, you can set up to IEC. My study type, I can toggle between a 3-phase device evaluation, and then I could also consider my single phase and look at all my single phase portions. Here are all my reports, and the purpose of this section is just so that you can analyze one report at a time if you wish. So if you only have one scenario, you want to look at full details, you can just uncheck all of these and then look at the full details of your maximum, your single report. And this is similar to any of you guys that are familiar with your ArcFlash result analyzer. It's a very similar concept. So if you use that one, you can navigate through this one easily. So again, single report gives you full informational data. The purpose of multiple reports is that you can do a comparison quickly and avoid using any post-processing analysis or just looking at multiple reports at a time. So this tool just gives you on the fly. So I'm gonna go ahead and leave it here. Now the selection section, you can have general and then device duty. Let me show you general, and I can enable all my reports here. Now this general section is just based as the purpose is to give you a summary of all the scenarios that you've executed, and it gives you all your full scenario configuration. So what study case you use, the study type, what revision you use in that scenario, the configuration, how many buses and branches were in service during that study, any pre-fault voltage considerations, and then as well as equipment cables, any specific standard that you use. For here's C37.010, and then any adjustments. So it gives you a full summary. Now we're interested in the device duty. So if you go to selection device duty, this gives you all result and input data for your equipment. So here, right next to this section here, you have your device type, and you could toggle between your various devices: buses, HVCBs, low voltage circuit breakers, any generator circuit breakers, fuses, and switches. And this section right here in the middle gives you informational data, which is all input data that you've placed into your elements, and then result, anything that was calculated by the program. You can toggle between for multiple reports. But if you're using a single report, you can just add columns. So let me go ahead and show you that. You see, so all of these columns are added to from your results, and you have a summary of this report. Now the alert section gives you critical and marginal alerts, and the neat thing about this is that you set your global limit to, so you don't have to rely on the study case alert section. You could just set a new limit for your alerts here. So if I set this to 200, now I've raised my limit. So now I just want to look at all of the equipments that exceed even 200% as opposed to 100. So that's the neat part about this section here. The same goes with marginal. And if you don't like red or magenta, you can go ahead and change it. Just click on the color and you could set different colors that you need. So now if I want to consider all of my scenarios here. Now I have my duty analyzer. I want to do my worst case. So all you have to do is select the worst case option here. And then this gives you worst case scenario. It's going to give you your worst case for symmetrical, as I have here under results, along with the output report, configuration, and revision that gave you that worst case duty results. And the same goes for asymmetrical and then peak. So now if I want to further filter out my results, I can click on skip not alerted devices, and this gives me a full summary of my worst case peak conditions and only those buses that have been critically and marginally alerted. So now I can simply export this to Excel by hitting on the top left corner, then doing Control C for control copy on my keyboard, and I can export this to an Excel sheet by just pasting my results. So now anything that you've configured in your short circuit duty analyzer, you can export to an Excel report for your for your analysis. If we go back to the short circuit result analyzer, we can follow the same procedure when analyzing other equipment that's attached to your buses. For example, if we're going to be looking at all the high voltage circuit breakers and we want to identify the worst case, you could just simply go to HVCB, and I want to look at all my momentary peak worst case conditions. I could also then toggle to look at my asymmetrical or interrupting adjusted symmetrical, and then just skip all the devices that are not alerted. So here I can see worst case for interrupting HVCBs. Similarly, you can go ahead and inspect all your low voltage circuit breakers here, and you could even identify the type of the LVCB, even look at the rated interrupting and the test power factor, and what bus it's attached to. So if I want to sort all my breakers for specific buses, I can do so, and then have my worst case enabled. And again, skip anything that's not alerted. And we can go ahead and show you the fuse, same concept with worst case, or if you want to compare across all reports, or simply just leave your worst case, and also with switch. Now if we're looking at the high voltage circuit breaker, you could still identify any adjustment factors across reports used for the interrupting capability or for the momentary. And these are just across the reports, and notice that the analyzer knows that there is no worst case comparison for these results, so it simply just hides the alert view. If you go back to a result that's actually a calculated short circuit result, you can see your alert and you can enable your worst case. Now the analyzer will also have capability of doing IEC buses and IEC equipment attached to those buses, as well as single phase. So very quickly, I'll just go ahead and run a IEC scenario, and we'll do a IEC duty scenario for this case, and I could go ahead and launch the analyzer and simply put my standard to an IEC standard. Here you'll notice that I have my my results for the single report for all my buses, and I'll be looking at the initial symmetrical, the peak, and then the steady state symmetrical value. You could also look at the high voltage circuit breakers and look at all the capabilities for these high voltage circuit breakers, as well as the thermal result. And the same goes for low voltage circuit breakers. In this study case, I don't have any low voltage circuit breakers, only high voltage circuit breakers and buses. But it'll be the same concept for ANSI and IEC, and you could go ahead and toggle back to ANSI standard and just look at all your scenarios for ANSI that you have configured. This concludes the technical webinar on short circuit result analyzer. I hope you've enjoyed it, and hope you learned something from the minimum and maximum scenario configurations and doing the analysis with the short circuit result analyzer.